I want to talk about something called the Cauchy identity. It's a famous identity and of great significance in a lot of subjects. And I'll define the concepts on the right-hand side. These are the Schur polynomials, this product. Okay. So this identity, what's its significance? Well, among the significances is that it's equivalent to Schur-Weyl duality. So if you're interested in representation theory of general linear groups and symmetric groups, the fundamental relationship between them as expressed in Weyl's book on the subject is equivalent to this statement. If you're interested in linear algebra or invariant theory, the fundamental theorem, first fundamental theorem of invariant theory for general linear groups, which talks about what are the generators of the invariant ring, is equivalent to this statement. If you're in algebraic combinatorics, as I am, then this is equivalent to something called the Robinson-Shenstedt-Knuth correspondence, which I will soon talk about. Okay? But what I want to do today is I want to look at the definition of the identity or the statement of the identity and basically interpret it in three different ways. One is just a statement of generating series. B is a statement about representation theory. And I will define all the representation theory concepts that I need. In particular, for those who are experts, how a torus character can be reassembled as a GLM cross GLN character formula. That's another way to interpret it, and I'll explain that. And then C, in terms of commutative algebra. In other words, that a Hilbert series is equal to the same thing as before. Those are three interpretations that I'd like to discuss about this old identity. And what to do here. And what's the goal of our project? The goal is to generalize these perspectives. To what? I'll be a little bit vague for a moment, to certain affine varieties inside matrix space. That's the plan. Okay, so let's talk about generating series first, part A. The left-hand side is the generating series for m by n matrices of natural numbers. So for example, I might have 0, 1, 1 plus 1, and 1 plus 1 plus 1 as my 2 by 2 matrix. And what's the point? The point is that I want to charge a cost, let's say here, of using 1 as x2, y2, because those are the coordinates of that position in the matrix. But I want to do it to the third power because there's 3 of them. And similarly, I want to charge x2, y1. You get my point, I hope. Squared, et cetera. And you multiply these monomials together, and that's the cost of this matrix. And that's why you have, by the geometric sum formula, 1 over 1 minus xi yj, depending on how many 1s you see in a particular position, right? And you're multiplying them because you're charging the product of such monomials to your matrix. So that's the left-hand side. And I want to make one trivial remark that is important for us later. I want to just observe that to such a matrix, I can assign a monomial in the z's. So z, this is the exponent vector of some monomial in the z's. z12 to the 1, z21 squared, and z22 cubed. Okay? The obvious way. Okay, so keep that in mind later because we'll be using that fact. What about the right-hand side? Well, on the right-hand side, we have these things called Schur polynomials. And a Schur polynomial is about semi-standard Young tableau. What's a semi-standard Young tableau? In this part of Canada, anyway, we draw them with some sort of partition, weakly increasing along rows, strictly increasing on columns. Fine. In this part of the country, minus York. And we have some sort of entry such as this. Right? And the cost of the tableau is x1 to the number of 1s, x2 to the number of 2s. There's 3 of them here, and so on. The Schur polynomial is the generating series for all such tableau of shape lambda. This is my partition lambda equals 4, 3, 1. Where you charge this sort of cost to every tableau. And this happens to be a symmetric polynomial, although not obviously from the definition. So if we look at the right-hand side, that means this is a product over this generating series. So interpretation is that to every matrix, you can associate a pair of semi-standard tableau, P and Q. Semi-standard tableau of the same shape lambda. That's what that says. And so the question is, what is that algorithm? That algorithm does exist explicitly. It's called RSK. Robinson, for a University of Toronto professor back in the day, Shenstead, and Knuth, of computer science fame. Let me do this particular example. So just to erase this is 1, 2, and 3. And what I'm going to do, I'm going to state the Robinson-Shenstead-Knuth correspondence slightly in an unorthodox way, but let's just do it. I'm going to have 2 reading words. I'm going to read down a column, and I'm going to, I should have kept it as it was. Okay, so I'm going to look at this 1 plus 1 and say, which row does it appear? It appears in the second row. That one appears in the second row. This one appears in the first row, second row, second row, second row. So I'll create a word in this way. We'll call that a row word. And another thing we're going to do is we're just going to read normal English, and we're going to calculate columns. So if I read along columns, I see this one appears in the second column. This appears in the first column and first column, so 2 1s in a row, and then 3 1s in the second column. We have 3 2s. So assigned to any matrix is a pair of words like that, and then there's something called row insertion that allows you to compute a tableau out of this. The tableau here would be 1, 2, 2, 2, 2, 2, and then this is one of my tableau. This is P, and then the other one would look like this. This is Q. So there's some specified algorithm that we won't go into the long details of for giving such a pair of tableau. That's Robinson-Knuth correspondence in a nutshell. And that answers what the generating series interpretation is. It means that there's a bijection between objects counted from the left-hand side to objects counted on the right-hand side that they are the generating series for, and we prove this equality by giving a bijection. Okay. Any questions so far? Yes? Yeah, sure. Well, okay. So let me at least tell you It's called row insertion. It's this ingenious idea of Shenstedt, who was a physicist. And you basically start reading, you put numbers in, 2, and then a 2, and then this one bumps the 2. It's a little bit annoying to say. It's not hard. I think within 2 minutes of reading a Wikipedia description, you will understand, but it's a little annoying. Another way to say this that's standard to the theory is that there's a Knuth equivalence class of these words, and this is the unique Knuth equivalence class whose reading word is equivalent to this. There's 2 ways to state this, and then there are a bunch of other algorithms that also compute RSK. That's some of the things that people have done in the subject. Okay, B. Let's talk about representation theory. Okay, so I want to interpret this in terms of representations. Well, what is a representation? A representation of groups means that you're trying to represent each group element as a matrix, and we are writing down a homomorphism from your group G to invertible linear transformations of some vector space V. Usually in the textbooks, V is finite dimensional. And if you go infinite dimensional, then you can get into all kinds of worries. We will go infinite dimensional, but in kind of a very mild way. So the nuclear option is that whatever I say that sounds infinite dimensional, we can always reduce to the finite dimensional case. So everything will be fine. There's a homomorphism. And this is equivalent to saying that there's a G module structure. In other words, the group algebra of G module structure on V. Okay, what do I mean by that? I mean that if I want to ask how does a group element V, G act on a vector V, then I compute the matrix associated to the group element, and I let that eat the vector V. Equals. Okay, so that's what that is. And there's a sometimes scary word that shouldn't be so scary here. It's when G is good. Well, G is good means reductive. In this case, linearly reductive. But what does that mean? That means that in our context, that means we get combinatorics in the following way. That if I have some sort of representation V, which I'm just going to either go back and forth in the homomorphism description or the vector space description of a representation, then this decomposes into a direct sum of irreducibles. So it's over some indexing set, Vi, and with some multiplicities. Okay, so these are irreducible representations. That means that there is no G-invariant, proper G-invariant subspace. What are these MIs? MIs are multiplicities, but we can be very specific. This is the same as the dimension of the space as a vector space of G equivariant maps from your irreducible variety into V. Okay, so in pedestrian terms, just the number of times Vi appears, so to speak. Yes? It's some indexing set I'm leaving as abstract. Like there is some indexing set, let's say, of irreducibles, and then you're able to decompose into them. Okay. So what example do I want to think about first? It's the example of the example I want to think about that's crucial is that a G is the same thing as complex numbers minus 0 to the rth power. Okay, so this is what we call an algebraic torus. Strictly speaking, I'm talking about isomorphism with, but let's just say it is just literally that for simplicity. And this is the subject of a very important fact. This is an abelian group, and therefore the irreducible representations are one-dimensional. They're all one-dimensional, and we can even say exactly what they are. So we're talking about lines here. And they are, in homomorphism terms, something that takes a collection of R complex numbers and shoots out a monomial like this, where alpha 1 to alpha R is some tuple of integers. These are the irreducible representations, at least the rational representations. And we can also say what we mean in terms of vector space terminology. This just means that if I take something like this, where I write down some matrix T1 to TR, and I'm acting on a vector V, then I get T1 to the alpha 1, T2 to the alpha 2, TR to the alpha R times V. So it's an eigenvector. Terminology, this is called a weight, and we'll call this a weight vector. The weight vector means it's one of the vectors that spans the particular one-dimensional representation. Okay? All right. With that standard terminology, let me now try to explain the left-hand side again. So we're again in part B, representation theory. I want to talk about the left-hand side. Okay, let's talk about the left-hand side as follows. I have matrix space, m by n matrices. And there is an action of general linear group cross general linear group. In other words, row and column operations on matrices. This obviously acts on matrices. And I can also take the diagonal matrices inside here. And it will also act because it's a subgroup. This means that you also have an action on the coordinate ring, the ring of polynomial functions on matrices in the usual way, right? I mean, a group element acting on a function, you're asking how it eats a vector. This is the same as the function G inverse the vector. That's the usual way of describing an action on a coordinate ring given the action on your vector space. Okay. So this is an algebraic torus because it's isomorphic, it's isomorphic to C star to the m plus n. So it falls into the situation over there. And now let's just, again, think about the monomials inside here. A monomial, like the one I had, z1, 2 to the 1, z2, 1, 2, z2, 2 cubed, this is a weight vector, right? It's a weight vector with weight 1, 5, 2, 4. How do I know that? I know that because it's the exact same weight as the generating series weight. The cost of our matrix, 0, 1, 2, 3, was x1, y2, x2, y1, x2, y2 cubed, and this is equal to x1 to the 1, x2 to the 5, x3 squared, x4 to the 4. As long as, oh, sorry, what am I doing? y1. Thank you. Okay, so I'm just reinterpreting the sort of quote-unquote natural generating series description of matrices in terms of weights. Now the monomials that span this vector space of matrices, which I'm identifying, of course, with Zij, the polynomials in m by n variables, has those as a basis, and they are in fact weight vectors. That's your decomposition of this infinite dimensional representation into one-dimensional pieces. And we are just simply saying, well, what is that thing? We're going to sum over these weights. Oh, what does sum over weights mean? Oh, let me keep that there. I forgot to say one other standard thing to say. I'm not done with the interpretation yet, right? What's a character? A character could mean many things, but in this particular context, a character just means the generating series over all the weight vectors with respect to their weights. With respect to their weights, in the sense of representation theory. But what I've tried to argue in this board is that the weight in terms of representation theory is the weight that you think about in terms of combinatorics. So therefore, obviously, all I've done is restate this generating series expression and said that it's a character. But that at least brings us into the land of representation theory. Okay? Any questions so far? I know this is like a 5-minute explanation of the basics of representation theory if you haven't heard them before. But are we good? Okay. Yeah? You won't offend me if there are any questions. Okay, good. No? Okay. Now that's if we think about the action of the torus. That's because that's the standard approach in this kind of representation theory. You want to understand a representation of something more fancy, like the general linear group, and the standard modus operandi is to first look at the restricted action of the onto the torus, because that has the one-dimensional representations, and then hope to sort of reassemble the information from knowing the torus decomposition into understanding the representation of the more fancy thing. And that's what we're going to do here. But let me just tell you some facts about GL. Okay. Well, first fact is invertible linear transformations, invertible matrices. That's a definition. One, GL is reductive. This is complex numbers. It's reductive. So it has the nice properties where we can talk about decompositions of representations into irreducibles and talk about counting multiplicities. The second thing is that due to a thesis of Schur, of the same name for the Schur polynomials, we know the irreducible representations exactly. The polynomial representations, what we call polynomial representations, the rational representations, and essentially the ones that you could possibly care about. So Schur tells you that the irreducible representations, which we'll call V lambda n, are indexed by partitions with at most n rows. In this talk, we're not going to inspect the actual construction of those representations. They're found in many textbooks, and there are many conversations we could have about it, but we won't get into that in this particular lecture. And then the third thing is I'm interested in not just GLN, but I'm interested in GLN cross GLM, right? And it's a general fact of that it's a quite general fact that if I have a product of two groups, and I know the representation theory of one group I know the representation theory of the other group. Let's say I know all the irreducibles, then I know all of the irreducible representations of their Cartesian product. The irreps are all V lambda n exterior tensor product V mu m. So you take the representations, the irreducible representations of GLN, irreducible representations of GLM, and take their external tensor product. What's the action? If G and G prime are my group elements, the action on a vector is just what you think, like that. And there are no other irreducibles. Okay. So since we're assuming, or since we have that there's this action of these groups on this thing, this is a representation not only of the torus, but the representation of a product of general linear groups. So therefore, as a representation, matrix space decomposes as a, let's just call this GL. Direct sum over these irreducibles. With some multiplicity. And that's just from knowing nothing. But what Cauchy's formula is saying, right, is that actually Cauchy is equivalent to saying the following thing, that m lambda mu is equal to either 0 or 1. It's a multiplicity-free decomposition. It's 1 if lambda equals mu, and 0 otherwise. Why does it say that? This is because the reason why Schur polynomials are called Schur polynomials is that they are the torus characters of these representations that Schur found. Right? They are GLN representations. The standard trick is you think about the torus action instead, the diagonal matrices. You decompose those. A character, I taught you, is by definition the generating series over the weight vectors. And the statement is the Schur polynomial is that character. And this character theory is very, very strong. It behaves well with respect to direct sum. It behaves well with respect to tensor products, internal and external. And so therefore, this Cauchy identity can therefore be interpreted on the right-hand side as really being a description of this decomposition as GL modules. And since, what does the equality mean? The equality means that if I have this GL decomposition, I can think of it instead as a torus decomposition, because I can just think about restriction, and that's the meaning of the equality. And so therefore, both sides have representation theoretic meaning. Okay, C. In C, I want to just reinterpret one more time the left-hand side in terms of commutative algebra, all right? And hopefully explain a fact that is well known to everybody who does this stuff, but I think is less well known than it should be. Okay, so we're going to reinterpret left-hand side. Reinterpret left-hand side one more time. Okay, so let's suppose I have an affine variety sitting inside complex n-dimensional space. In fact, I will assume that this is going to be defined with equations that are homogeneous. So in other words, this is an affine cone of a projective variety. AKA defined by homogeneous equations, degree homogeneous equations. Another way to say this is that this is equivalent to saying that I have a C star action, okay, on X, which if I have X1, X2 to X, oh, let me not make that N, let me make this capital N, Xn, and I want to know how an element of complex numbers acts, is just rescaling simultaneously each one of the coordinates. Okay. Right, so affine cone over projective variety means that you're defined by homogeneous equations. It obviously also means that this is an action. Okay, under any of those equivalent assumptions, we can talk, as Hilbert does, about the Hilbert series. What is the Hilbert series? It's another generating series. It's a Hilbert series. We'll give it some notation. Hilb, X, T. Well, okay. I mean, this is going to be the sum over D positive, let's say. And let's look at the coordinate ring, the ring of polynomial functions on X. And since it's homogeneous, we can talk about the d-graded piece and look at its dimension as a vector space, it's vector space dimension, and record those dimensions. These are all fine dimensional. That's the Hilbert series. Okay. This is the definition. But what this is equal to is this is the same thing as the torus character of this coordinate ring. This simple fact relates commutative algebra to representation theory. Okay. If C star acts on my variety, it acts on the coordinate ring by this, inverse type thing. And so therefore it has a character. If you just think about the definition of this, of what it means to be a character, that's the same as thinking about this as this Hilbert series description. Okay, so the only point that I want to make at the end of part C is that therefore the left-hand side is some Hilbert series. And it's equal to some right-hand side, which is representation theory. Okay. All right. I want to now talk about what our results are to try to extend this story. Any questions about the setup? Well, Cauchy identity is about matrices. And here I've been saying that matrix is a vector space, but it's also a variety. It's an affine space. And one of the things you can naturally do is, well, I mean, you could think about just some variety sitting inside matrix space. Okay, but fine. And then the next thing that we took advantage of in the ABC conversation is that this has an action by row and column operations. Okay. So it's reasonable to want to make the same assumption here. Let's think about varieties X with a GLM cross GLN action and study that. And is there a problem? There's absolutely no problem. But under that assumption, GLM cross GLN acting on a variety X you actually only get one type of variety. A very important variety, but only one type of variety. This implies X is a determinantal variety. It's going to be the space of rank less than or equal to K matrices inside matrix M cross N space. And this has been the subject of many studies. Bernd Sturmfels, in a paper early in his career, studied this, and he was able to give a proof of a Grobner basis description of the ideal that cuts this out. In other words, the rank K plus 1 by K plus 1 minors of a generic matrix is a Grobner basis. Now, what is some of the significance of such matrices besides them being seemingly ubiquitous throughout commutative algebra and algebraic geometry? Well, one of them comes back to invariant theory. I mentioned briefly the first fundamental theorem of invariant theory for GLV acting on vectors and covectors. Okay. I don't want to say too much about this, but that means that we can talk about the coordinate ring of this. And we can talk about this acts on the coordinate ring, and we can talk about the GLV invariance. And there's something called contractions. I won't define them here in terms of ZIJs, let's say, that generate this as a algebra. Hilbert says that all such invariant rings must have a finite list of generators as an algebra, and these contractions give it. What are the relations between these generators? That's also a question that Hilbert considered, and the answer is given by K by K minors in these contractions, Zij. And what's K? K is like the dimension of the vector space V. So this is very much has to do with invariant theory. And what Hilbert also considered was the question of not only what are the relations between those generators, but what are the relations between those relations, and so on and so forth. This is the subject of his theorem about finite free resolutions over a polynomial ring. And that has been resolved by Kempf, Lascaux, and Weyman. Sturmfels talks about the Grobner basis, and in fact does more, because what he does is he connects the study of Grobner bases to RSK. That was a wonderful insight in his paper, and in some sense, one of the things we're doing is in fact generalizing some aspect of that philosophy. If I have time, I'll say more about this issue here, because this is what really motivates our particular study. Okay, okay, so the upshot of what I just said is that if you assume your action is by GLM cross GLN, then you're getting the space of determinantal varieties, and those are, of course, well studied. So what does GLM cross GLN look like? It's some square matrices. Okay, so this is group action. And what we're going to do is we're going to think about a subgroup. We're going to take block matrices, each of which are invertible, along the diagonal. So let's say something like this. Okay, so this is a product of little GLs. And then over here, I'll take some other block decomposition. And my assumption, this is what we'll call this L and L prime. Okay? And we are interested in varieties that are stable under this sort of group action, so that we are walking away from just merely determinantal varieties. Okay? Sometimes these are called Levy groups, Levy subgroups, if you look up that kind of literature. Okay, so we're interested in this acting on X as my assumption. Any? Right, so I'm saying, give me your X which has an action of a Levy subgroup like this. So it could be that my blocks are everything, in which case I'll get determinantal varieties and we'll recover that theory. Or I can assume the blocks are all just one by ones, in which case we're talking about tori, and then we're talking about Hilbert series calculations, or multi-graded Hilbert series if you look up Ezra Miller and Bernd Sternfeld's book for that terminology. Okay, so we're assuming that. What else do I want to assume? Well, this one is a little bit of a technical thing. But I want to, I need to say the following words about Grosvenor basis theory, the topic of Barrett's paper. Just a little bit, because I know many of you are experts. And for those of you who are not, then I'm just going to say just enough to get my point across. For matrices, the monomials and the Zij's are the weight vectors. Remember, there's this sort of trivial correspondence between weight vectors and their weights, and then the generating series definition. I want to know what the weight vectors are for a variety X inside matrix space. So our coordinate ring of X is described as, if you put coordinates down, as polynomials of x1 to xn, quotient sum ideal I. Right, and I is I here we're going to assume, well, we make no assumptions except what's given by the fact that there's action, so it'll have some sort of homogeneity. Anyway, so what do you do in Grosvenor basis theory? You pick a term order. Right? And from that term order, that gives rise to an initial ideal. This is by definition all the monomials. This is going to be generated by the initial terms of every polynomial in I. So there's infinitely many such calculations, but then you take the ideal of them, so there's going to be finally generated by another of Hilbert's theorems. Okay, but what's the actual notion I want? I want to talk about the standard monomials. So I don't know what terminology I want. Maybe I want this. Okay? Standard monomials are the complement of the initial ideal. They're all the monomials that are not in the initial ideal. So remember, we're working inside this polynomial ring. I'm looking at monomials in here that are not in the initial ideal with respect to my particular term order. Okay? And the basic fact of Grosvenor basis theory is that the standard monomials are a vector space basis of the coordinate ring. So this is the statement that allows you to conclude things like the Hilbert series of the original variety and its degeneration are the same thing. Grosvenor degeneration, if you like. But I would simply like to reinterpret this statement as a statement about weight vectors. The standard monomials are obviously the weight vectors of a torus action. What torus action? Is the torus that sits inside these block matrices. The same torus, diagonal matrices. This is a basis of weight vectors. Okay. Any questions? All right. So at the beginning of the talk, I said that for certain varieties in matrix space, I want to be able to extend A, B, and C. Here's the definition. X inside matrix space is what we call bicrystalline. If it has a Levy action, a rational Levy action, meaning it's an algebraic action. So that L cross L prime, and a technical hypothesis. And the technical hypothesis is that there exists a term order such that the standard monomials with respect to that term order is closed under what are known as bicrystal operators. Okay. Bicrystal operators. Now, what are bicrystal operators? I don't have the time to explain the whole thing, but let me just say the following words. When you're trying to understand representations of general linear groups or complex simple Lie algebras or semi-simple Lie algebras, there's a very strong understanding that was developed by people like Lakshmi and Sheshadri, by Littleman, and by Kashiwara. The combinatorial version is that the semi-standard Young tableau are not just a set, they actually form a graph. And this graph has representation theoretic meaning. We could get into it, it's a very wonderful story. And so you can sort of connect a semi-standard tableau of a given shape by these Kashiwara raising and lowering operators, not defined here. On the other hand, RSK connects semi-standard tableau to matrices. So what Danilov and Koshevoy and simultaneously Van Leeuwen did is they basically pulled back Kashiwara's operators to define a bicrystal graph structure on matrices. Okay, so that's what we're talking about. And remember, standard monomials, remember at the beginning of the talk I said, remember, a matrix is the same as a monomial. So under that recollection, we can think of this as a space of matrices, a collection of matrices of non-negative integer coefficients. And I'm asking that these operators, which I did not define, that come from Kashiwara and his fabulous theory in combinatorial representation theory, fixes this set. Now I'm dropping a detail or two, I'm lying slightly, but this is the essential point. Okay, so this technical hypothesis, I think is rather a weak hypothesis. Now, it's strange because it's got so many words to it, so whenever you have so many words, usually means a strong hypothesis. In actual fact, I think that I know no examples where we need this hypothesis. That's how weak I think the hypothesis is, but I cannot prove that we can remove it. All right, but in any case, everything that we're going to use this sort of definition for will satisfy the hypothesis. Okay, theorem. Let's let X be bicrystalline. Okay. Then its coordinate ring is isomorphic as an L cross L prime representation to some direct sum of irreducibles. So this thing means a collection of partitions because really each of these is itself a product of general linear groups with some multiplicities. So very much analogous to the classical story. And what we can do is we can give a rule for what these multiplicities are. M lambda mu is equal to the number of standard monomials that filter RSK to highest weight tableau, which I have not defined. And depending on how much time I have, which is almost none, I may not get a chance to. So in my last 45 seconds, I'm sorry, I'm happy to show you this, it's not so bad. To connect to Patricia's talk, the other theorem that we have by the same authors is that matrix Schubert varieties are bicrystalline with respect to a certain natural Levy action. And so therefore we can apply this theorem to those varieties. In the case that X is a matrix space, this is Cauchy's formula. In the case that this Levy action is a torus, this is multigraded Hilbert series. And in particular, in certain cases, you get back the Littlewood-Richardson coefficients. So this rule here is a generalization of those numbers. Sorry, I'm over time, so I'll just stop now.
Any questions for the speaker?
That was a really nice talk, Alex. I liked it a lot. I didn't understand what was happening over on the right-hand board. So if I have my term order, I have my my standard monomials. How do I cook up the Levy subgroup so that the standard monomials are the weight vectors?
Right. So every one of these Levy subgroups contains diagonal matrices. The diagonal matrices are a torus, and weight vectors are only a concept assigned to torus actions, which is this method that we have in representation theory to sort of understand a representation. So this is weight vectors with respect to the T cross T prime action. The diagonal matrices here inside and the diagonal matrices there. It's just an interpretation of a Grosvenor basis statement in terms of representation theory. It's a trivial observation about how you can reinterpret that standard theory in Cox-Lewis-Shea.
Okay, thank you.
Yeah, so what's special here is, yeah, sure. So what's special here is the term order. That has to be adapted somehow to your Levy is decomposition. So you're sort of picking up, because, I mean, you want to so you're picking, like, say, upper triangular or something for the raising and lowering operators. So there must be something special in that term order.
Okay, yeah.
Not just any term order.
Right. So excellent question. So what is the connection to the earlier conversation? In the case of GLM cross GLN, if I say abstractly, let's think about varieties with a GLM cross GLN action, there might be many, right? And in fact, there aren't. There are only determinantal varieties. Very important varieties, but only one family. It's plausible that when you impose a sort of Levy action, there are only certain kinds of varieties that can occur. And for those varieties, this theorem would hold anyway. The term order would mean that, like, under any term order, it would be true. Because under any term order, you compute, let's say, the degree. You would get the same answer. It's not totally implausible.
So if your Levy group is just a torus, so 1 by 1 blocks, what does bicrystalline mean? Is it automatically satisfied?
It's automatically satisfied because in the definition that we kind of hid, there are no, so what's really going on is they have to be closed under the bicrystal operators with respect to the Levy that you chose. And in the case that it's a torus, there are actually no bicrystal operators, so it's vacuously true.
I'm still troubled by you taking any term order.
Well,
You can take any order of the M times that variable and flex of that. You get really radically different standard monomial.
mm-hmm.
I guess the bicrystal operator is position in the term order as well.
That's right. It's in existence of a term order such that it is closed under these operators. So it's possible that it's true under some term orders and not true under some other term orders. But just to make you feel a little more comfortable, right? That's right. So in the case of our theorem over here, it's bicrystalline with respect to the Knudsen-Miller term order. Right, so we're using their theorem in order to prove this statement. But I mean, maybe just to make things a little, just to say something to the audience, the Hilbert series is a character. That's one of the points I was trying to make in part B. And so you compute Hilbert series, let's say computationally, by choosing different term orders and choosing some term order, but they all compute the same generating series, and therefore they all compute the same character. Therefore, a priori, it's possible that if you drop this hypothesis that, choose some term order, find standard monomials, compute the ones that filter RSK to that thing, and then you get the same decomposition. Multiplicities, that is, multiplicities.
certain, maybe this is, well, okay, I don't know much about the Knudsen-Miller part that you cited, but for the choice of W, for XW, is it sometimes just that it's bicrystalline with respect to the one by one? Like, do you always get a non-trivial or a non?
That's right. We're saying nothing new about Hilbert's series of matrix Schubert varieties, because in that case, the bicrystalline hypothesis is vacuously holds. In all other cases, we're getting extensions of the Hilbert series formula by this sort of thing, depending on your choice of levy. So you have an interpolation from the largest levy that acts on your matrix Schubert variety all the way down to the torus action.
So you started with the Cauchy identity, which is an identity between two ways of computing two characters, essentially. So here, what would be the identity that you get?
The identity would be, on the one hand, you have a levy action, and you compute the
Which is the right-hand side.
the right-hand side. And on the left-hand side, you have an interpolation of all of them. You have equality for every subgroup, sublevy, all the way down to the torus.
Any other questions? All right, let's thank the speaker again.